So let's examine working with equilibrium constants. What kind of information can they tell us about where a reaction is at any particular point in time? So let's just review calculating an equilibrium constant. And in this particular problem, you're actually given the value of the concentration of both our products and our reactants at equilibrium. So the first thing you want to do is simply assemble the equilibrium constant expression, which in this case is going to be products, which is nitrogen dioxide. We're going to square that term, divided by our reactant, which is the dinitrogen tetroxide, into O4 to the first power. And then since they've given me something that they're specifying as the equilibrium concentrations for these two guys, all I have to do is plug them in and do the math. So for nitrogen dioxide, I've got 3.00 molar, and I have to square it. And then for the dinitrogen tetroxide, I've simply got 3.00, and that's just going to give me 3 squared, which is 9 over 3, and that gives me an equilibrium constant of 3. So K is simply equal to 3. I guess maybe I made that question too easy in class. You better get it to 100%. So let's take that a little bit further and determine the direction of a reaction. That is, if the reaction is at equilibrium going backwards, what does that mean? That means that the rate of the reaction in the forward direction is equal to the rate of the reaction in the reverse direction, so that these concentrations, concentrations on both sides of the reaction are constant. That means that it's going in the reverse direction at the same rate as it is going in the forward direction, because this is constant concentration and this is a constant concentration. As fast as the dinitrogen tetroxide decomposes, the nitrogen dioxide combines with itself to form the dinitrogen tetroxide. These two rates are equal to each other. So let's use the equilibrium constant to determine the direction of a reaction. So if you're given an equilibrium constant, we know what the final ratio of the products to the reactants are. That is the equilibrium constant. That is the ratio. So K is equal to that ratio of, and this is the way we do it, products over reactants. Now, if we're not at equilibrium, we can actually calculate something called Q, the reaction quotient. And based on the magnitude of Q, is it greater than K or is it less than K, we can predict which direction the reaction is primarily having to go in order to get to K. Because what you want to remember is that the equilibrium is the lowest energy point in a reaction. It's all about energy with respect to equilibrium, It's sort of like the bottom of the hill. All right, so reaction quotient Q. Q, the reaction quotient, temporary state of the reaction. Remember, it's temporary because the reaction wants to be at equilibrium. It wants to be at K. So you simply calculate the Q exactly like you do the K. That gives you the ratio at a moment in time, and that will tell you whether the reaction needs to go further toward products or back toward the reactants. Remember, Q is calculated exactly the same way as K is calculated. So you can think of it like this. I know this is crude, and I already had to draw it because if I drew it freehand right now, it would be eminently messier. So this is energy of your reaction on the y-axis. So energy, you can see from my writing here why I went ahead and drew this ahead of time. So here's the deal. So let's say we start the reaction with only reactants. And if we start with only reactants, there really is only one way to go, and that is in the forward direction to make products. Now, as products are being made, they build up their concentration and they start to run in reverse in an equilibrium process to make some of our reactant A. But if we haven't gotten to equilibrium, it's still going to principally have to go more in the forward direction than the reverse direction. You can think of it as a ball rolling down a hill. If the ball is sitting up here at the top of the hill, it's going to roll in the forward direction until it gets to that lowest energy point where the forward reaction is equal to the reverse reaction, till Q is equal to K. We call that equilibrium, where the forward reaction rate equals the reverse reaction. It's the low energy point in our equilibrium process, and that's where Q is equal to K. So if we're over here, the reaction's primarily going forward. That's where Q is less than K. That means that we haven't made enough products. We need to make more products. We need to have fewer reactants until, in order to get to the equilibrium concentrations for both products over reactants. And those are stable concentrations. As long as we don't change the temperature, change the volume of a container, as long as we, those concentrations will remain the same, okay? They're constant. On the other hand, let's say we started the reaction with a mixture of reactants and products, or maybe just with what ultimately we're designating as products. That means the reaction is going to run in reverse until Q is equal to K. So initially over here, the current state will be Q is greater than K. And we need to make more reactants. We need to have fewer products. So this concentration would need to come down. This concentration would need to come up until we got to the equilibrium ratio, okay? So Q tells you how close a reaction is to equilibrium and on which side of the equilibrium the reaction is. Hope that made sense. So, example, reaction quotient. We've got 1 mole of dinitrogen tetroxide. We mix it with 2 moles of nitrogen dioxide in a 1 liter flask. And that's just for our convenience, so we can call them 1 molar concentrations. So we're going to calculate the current state of the reaction. In other words, the reaction quotient. Now, I've conveniently given us the equilibrium constant expression. All we have to do is put the current concentrations in here. So it says nitrogen dioxide has 2.0 moles per liter. Remember, we've got to square that term. And down here for dinitrogen tetroxide, I've just got 1.00 moles per liter. And I calculate that. 2 squared is simply 4, and then 1 to the first power is 1. And so our Q is equal to 4. So here's what we're going to do. We're going to take our Q, and we're going to compare it to K. K in this reaction is given, the equilibrium constant is 0.5. So this is 0.50. And Q, we know, is 4. So Q is greater than K, and so the reaction is going to proceed in reverse. It has to make more reactants in order to get to equilibrium until Q is equal to K, which is 0.5. So let's go back to our little diagram here. And so what we've said is that this reaction quotient is 4. The equilibrium constant is 0.50. This means that in our reaction quotient, our product concentration is too large and our reactant concentration is too small. So we need to run the reaction in the reverse direction in order to get to the equilibrium constant of 0.5. Okay, this concentration needs to come down. This concentration needs to come up. The reversal of the equilibrium reaction. The meaning of Q. Q is compared to K to determine the direction of the reaction. If Q is less than K, the forward reaction happens to the greater extent. We need to make more products. If Q is greater than K, the reverse reaction. We need more reactants to get to equilibrium. And if Q is equal to K, you're good to go. The reaction is at its low energy point. The reaction will always proceed until you get to equilibrium, where Q is equal to K, because that is the lowest energy point of a reaction, and everything in the universe is trying to get to that low energy point. Here's another way to look at it. Direction of the reaction. Q, products over reactants. Reaction forms products. This is just that K is large compared to Q. Q is small. Q is less than K. So the reaction has to go in the forward direction to get to Q is equal to K. And this reaction, exactly the opposite. Q is larger than K. We need to make more reactants. We need to have fewer products to get to Q is equal to K. Just another way to visualize it. So let's try this, and then we'll call it quits on this video. Quiz, reaction quotient. In which direction will the following reaction proceed? We've got 1 molar of N2, 2 molars of H2, 3 moles of NH3. This is the Haber-Bosch process, and we've got a 0.50 equilibrium constant. So this is your problem. I will go ahead and I will set it up. We are calculating Q. And Q, in this case, since this is our reaction, is going to be the ammonia in NH3. Got a coefficient of 2, so we square it, divided by, and I'm going to go ahead and put parentheses around this, I've got nitrogen times hydrogen, H2. What's the coefficient of hydrogen here? It's 3, so I need to cube that. And all you have to do, ladies and gentlemen, is plug those values in to the equation. And as Nebula said in Endgame, all they have to do is not fall out on the way to Vormir.